Hello, welcome to The Naked Scientist with me, Chris Smith, and also with Kat Arney.
This week, we're peeling away at plastics, which are seemingly everywhere in modern-day life. But what exactly is a plastic? How is it affecting the fish in the ocean and us here on dry land? Plus, we look at whether the stats on recycling really are rubbish, and is recycling plastic worth the effort? And look into the future. Could farmers one day be growing plastic in their fields?
Also in the news this week, how scientists have found a way to read the burned Roman scrolls buried by the eruption of Vesuvius 2,000 years ago. We tour a new exhibition which explores the scientific legacy of Winston Churchill 50 years after he died, and how scientists are reading the magnetic signatures of meteorites to find out how they and our planet formed 4.5 billion years ago.
The Naked Scientist podcast is powered by ukfast.co.uk.
Roman scrolls, burned and buried 2,000 years ago when Mount Vesuvius erupted, are being read successfully by Italian scientists using a new technique that uses one of the brightest lights in the universe, an X-ray synchrotron beam based in Grenoble, France. Science reporter Jonathan Webb has been taking a look at the story.
These were dug up a couple of centuries ago from Herculaneum, which is sometimes called the Other Pompeii. It's a village that was similarly buried by the eruption of Mount Vesuvius in about 79 AD. But these scrolls are actually the only surviving library from those classical times. The tricky thing is working out what's inside them, because as soon as you try and unroll them, they start to fall apart. And there were various attempts to try and unroll them to varying degrees over the centuries. But these were mostly given up about 20 years or so ago because people decided that it was just too risky. And just this week, a paper came out where physicists actually managed to use X-ray imaging to look inside one of these scrolls without having to unroll it. And they even managed to work out what some of the letters were buried deep inside.
I've actually seen some of these scrolls because I've been fortunate to visit both Pompeii and Herculaneum, and you can go to the Pompeii Museum in Naples, and these things literally look like a hunk of carbon, and they are literally just charred remains. How on earth can someone read that?
Yeah, it's an almost unimaginably tricky task. And you're right, they were entirely carbonized, completely burnt by a blast of gas that was about 300 degrees Celsius. And so one of the main problems is that the stuff that is there in terms of a carbon-based ink and a burnt piece of papyrus is actually really similar. There's not a lot of chemical difference between the writing and the paper, if you like. So the key thing here was that the technique that the scientists used was called X-ray phase contrast tomography, which basically means instead of just the light and the shadow cast by an X-ray going through the scroll, they were looking at tiny variations in the speed, if you like, of the waves. They were actually able to see the 3D shape in an awful lot of detail, and it was the tiny little bumps, literally the little extra thickness that you get where there was ink as well as paper, that let them start to unpick a few of the letters from deep inside one of the scrolls.
Does this mean then that you can effectively, functionally unroll the scroll and read it eventually without actually having to unroll it?
That's the aim, for sure. And this is only really the sort of proof of concept. But the scientists would like to dedicate more time to this and get better at that unrolling process. It's really tricky to do all of that analysis, though, because not only is the scroll, thousands of years old and burnt and rolled up, but it was also sort of squashed and mangled. So those folds of paper are really in a sort of a twisted as well as rolled up form. So actually flattening it out using a computer and working out exactly what's there is a really demanding process, and it involves quite a lot of guesswork. So the scientists have to work together with people who know their ancient Greek letters to try and unpick exactly what's left there inside.
I've seen the paper that they're publishing, and actually the writing is quite nice. It's quite neat.
It seems to be quite neat, yeah. And it's interesting, they can actually start to see individual sort of styles of the people who had done the writing. Oddly enough, even though we're obviously in ancient Rome here, the writing is mostly in Greek in this library, and a lot of the texts seem to be Epicurean. They're from one of the early followers of the philosopher Epicurus.
And have they got any gossip from ancient Rome yet off these scrolls, or is it still early days?
Nothing particularly juicy just yet. At the moment, actually, it's only individual letters they've managed to pick out from within a scroll. But when they used a fragment that someone had already pulled off one of the other scrolls, they were able to use this technique to read complete words and start to put together sentences. So hopefully, as things progress and more time and effort goes into improving the technique, then we'll start to be able to actually read from beginning to end what's on some of these things.
I can't wait. Jonathan Webb on the ancient scrolls of Herculaneum.
Pah! Never mind the Romans, scientists have been using X-rays to look back even further into the past, to the beginning of our solar system. When the building blocks of our planets first formed 4.5 billion years ago, their molten centres made them magnetic. As they solidified, these magnetic signatures were left behind, written indelibly into the rock, for Richard Harrison and his colleagues to find. Georgia Mills went to meet him.
Well, we started to look at extremely old rocks. In fact, the oldest materials in the solar system, which are meteorites. So we're very lucky in that meteorites occasionally fall to Earth, and these are fragments of asteroids, which are parts of the solar system, rubble left over from the formation of the planets. And by studying these meteorites, we get to study ancient magnetic fields that were on the extraterrestrial bodies that these meteorites were originally derived from.
Looking at meteorites in this way has never been done before. It involved using an X-ray microscope, called a synchrotron, to examine the tiny pieces of metal inside the meteorite, which have recorded the long history of its magnetic field. But why look at meteorites in the first place?
We're interested in understanding what these bodies were like. So if you take yourself back to the very early part of the solar system, you have the birth of our sun, and it was in this sort of early period where the first protoplanets were forming. So we want to know what those bodies were like, how big they were, how hot they were, what structure did they have. And magnetism gives us a way of looking and peering into the interiors of these bodies by studying whether or not they had a magnetic field. Did they generate a field just like the Earth does? If they do, if the answer to that is yes, then we know immediately that these asteroids had a liquid metallic core very early on. That's one of the unique things we've been able to do with the new methods we've developed for studying this meteorite that allows us to track how the intensity of the magnetic field changed over time. And what we've been able to capture is the decay in that intensity over the period of time that coincides precisely with the time that we predict the core would have been freezing. So it's a kind of a remarkable find, really, that this particular meteorite we studied, and we've actually seen the moment at which the core finished freezing and the field then completely switched off. As soon as you have no liquid left, then the magnetic field dies. And that's recorded in the metal of these very unique meteorites.
And the Earth's core is itself in the slow process of cooling. Does this tell us anything about what we've got in store for us?
That's right, yes. The Earth also has an inner core. It's slowly cooling, and that inner core is slowly growing. It's about 1/8 of the volume of the total volume of the core now. And that freezing process is thought to drive our own Earth's magnetic field. So as that continues to freeze and eventually the entire core freezes, of course, we expect, if the analogy with our asteroid is a good one, then we expect the intensity of the Earth's field to gradually decay away. But the timescales are rather slow. So the Earth's core will not completely freeze for perhaps another 3.5 billion years, which is not something we have to worry about. But what we would predict on the basis of these results is that the Earth's magnetic field intensity would gradually decay away. The impact of that would be that the solar wind would encroach much closer towards the Earth and start to mess up with our communication satellites and all that sort of thing. So we can look forward to much poorer mobile reception a few billion years in the future if the sun hasn't already exploded by that point.
Oh, I'm used to that already, so it'll be fine. I suspect the mobile companies are delighted. They'll make even more money from people saying, you're breaking up. That was Dr. Richard Harrison. He's from the University of Cambridge.
You're listening to The Naked Scientists with Chris Smith and Kat Arney. In a moment, a new anti-radiation pill. But first, humans don't exactly have a good track record when it comes to preserving the delicate balance of nature. And Khalil Furlouet has been looking at two recent examples of how our presence can have unforeseen and unfortunate consequences for the ecosystem.
One of the reasons that humans have become the dominant species on our planet is our ability to colonise all sorts of habitats, from wet to dry, cold to hot, and high to low. We even change the environment to suit our needs, sculpting the land to build and farm on it. As our population grows, it inevitably leads to us bumping up against the local wildlife, which can have complex and far-reaching consequences, including diseases spreading to humans from wild animal populations, as was the case with Ebola. But this is a two-way street, and two papers published this week show how human presence can spread diseases among wild animals and also alter animals' behaviour. In Tanzania, dogs are implicated in an outbreak of canine distemper virus that wiped out nearly a third of the lions in the Serengeti National Park, as Mafalda Viana of Glasgow University explains.
At the time, we didn't know exactly what was the cause, but because distemper virus is a disease typically associated with domestic dogs, it was believed that it was these dogs that live in the villages around the natural park that transmitted the infection into the lions. So at that time, around 96, there was a vaccination program that started to vaccinate the dogs in order to not only protect the dogs, but also try and prevent infection into the natural park.
But there have nonetheless been several outbreaks of distemper virus in the Serengeti lions since. Were dogs still the cause?
In the beginning, it seems that the domestic dogs could have been the responsible for transmitting this disease into the lions. But since the mid-90s, we saw a change in these dynamics, meaning that the infection that would occur in the lions were no longer exclusively related to those happening in the dogs. And so what it suggests is that the dogs are not the only responsible for transmission to the lions, and that there's probably wildlife species inside the park themselves, in addition to the lions, that are maintaining the disease and causing these sporadic outbreaks.
But could this have been avoided?
Humans do need to live somewhere, and unfortunately it frequently creates these human-wildlife conflicts, but hopefully we can find ways of balancing the two.
Through vaccination, it's possible to prevent our domestic animals from becoming a reservoir for infection, both to us and local wildlife. But coughs and sneezes are not the only way that human habitation can affect the ecosystem. A team from the University of California, Santa Cruz, have been studying how housing in and around the mountains of the San Francisco Bay Area is affecting the behavior of another top predator, the puma, or mountain lion. Pumas hunt large prey such as deer, and will often keep returning to a kill to feed for a number of days. Normally, they don't stray far from their prize, but if they don't feel safe, they'll often retreat until the cover of darkness. Justine Smith.
A lot of places in our mountain range where we work are these low-density residential areas where houses are maybe 50 to 100 meters apart, and pumas are still using that part of the landscape to hunt and do all sorts of things. When they're near houses, they move far away during the day and sleep somewhere else and come back only at night to feed. And so these animals are able to hunt right up against people's homes, but they just won't hang around when they feel disturbed.
All this trekking back and forth wastes valuable energy, and combined with the loss of food to scavengers while they're away means that they need to kill more deer just to survive. This puts an increased pressure on the deer population in these areas.
Here, what we're seeing is really that the humans are sort of the behavioral top predator, if you will, that's changing the feeding behavior of the natural top predator, which is the puma.
But there are ways to limit the impact, with moves towards more clumped housing development which can be segregated from the puma's habitat, along with other measures to minimize the impact of our daily lives on theirs.
There has been a lot of attention in the development and planning world recently to look at more conservation planning when we think about designing new areas for development. In terms of places that are already developed, there are a number of potential options that could help. Constraints on what kind of light bulbs are there, how strong lights can be, sound ordinances might help to mediate disturbances to animals.
Let's hope so. Justine Smith and before her Mafalda Viana. They were both speaking with Khalil Thurloway.
When the reactor at the Chernobyl nuclear station exploded, some people were exposed to massive doses of radiation, resulting in lethal damage to the DNA in their cells. Now, scientists in the US have developed a drug that can protect against this level of radiation exposure, even if it's administered hours after the radiation dose. And apart from being useful in the event of a nuclear disaster, the breakthrough might hold the key to reducing the side effects of radiotherapy for patients undergoing cancer treatments, as Memphis University's Gabor Tigyi explained to Chris.
Radiation is everywhere. It's there not only in the nuclear reactors, but also in the nuclear bombs. But those of us who travel long distances on an airplane are exposed to a higher level of radiation than at the surface of the Earth. This radiation interacts with our cells, and above certain levels, it can cause damage. This damage usually leads to breaks in our DNA, and unless the cell somehow can fix and restore the blueprint, it may die. So repairing DNA has to be very efficient.
So how are you approaching that? What have you done to try to boost the rate at which cells can put damage to their DNA right?
We actually learned something by studying a very simple molecule called lysophosphatidic acid, generated in the course of blood clotting, that enhance DNA repair and, most importantly, increases cell survival after various harmful stimuli. It has a very short half-life in our bodies, and it's not like a drug that you can take once a day and then have a long-lasting effect. So what our research group has tackled over the years is to design a stabilized drug-like analog of this natural substance that can do all the things that the natural substance does: increase DNA repair, cell proliferation, and cell survival. This is in essence what has been accomplished.
And the chemical you've got, your drug candidate, how have you tested it? Just in a dish, or have you actually tried this for real in an animal?
Yes, indeed, we had extensive studies carried out in mice under various radiation injury scenarios, one that mimics damage done by radiation to the bone marrow, and also in another setting to the intestine. And in both cases, the compound was highly effective.
Would these animals, or the level of radiation to which these animals have been exposed, be equivalent to people who were working at Chernobyl, or equivalently, say, at Fukushima in Japan, where the nuclear meltdown occurred in the last few years?
Well, actually, radiation levels at the base of the reactor at Fukushima produced about a 10 gray radiation dose to those who are the robots that actually went into the vicinity. Our animals were exposed to 16 gray. It's a deadly level of radiation, yet we had very nice survival outcomes after drug treatment.
We often use radiation therapeutically, don't we? And people who have cancer, we can zap the cancer with a blast of radiotherapy, and this can be very effective, but it does have side effects. It damages healthy tissue in the process. Do you think we could use the approach you have come up with to mitigate some of the damage done to healthy tissue in a person having anti-cancer radiotherapy treatment so that they don't have so many side effects?
Indeed. What we are hoping to achieve in the next few years is to actually attenuate the collateral damage that is inflicted by the therapeutic use of radiation. For example, if you have breast cancer, radiation therapy is often used and does cause scarring and other side effects in the skin. So that's something that we would like to try to tackle.
Gabor Tigui from Memphis University.
2015 marks the 50th anniversary of Winston Churchill's death. And to commemorate the occasion and also to recognise the UK former Prime Minister's contributions, activities are being planned across the country, and among them is an exhibition at the Science Museum in London called Churchill's Scientists, which has just launched. Rachel Boone showed Kat around.
So Churchill's Scientists is exploring Winston Churchill's relationship with science during the Second World War and post-war period when he was in power. We look at his relationship with Frederick Lindemann, the first science advisor to government, and we explore the work of the scientists who were taken out of their research, put into a very unusual environment during the Second World War to develop drugs, to develop radar systems, to analyse attacks and to try and save ships from U-boat attacks. And then afterwards we look at what they did in the post-war period. What skills did they learn in that heightened experience of wartime research?
I tend to think of him as, the war hero with a big cigar rather than hanging around with guys in lab coats.
Absolutely. As a young child, he had quite a boyish fascination with science, but never achieved academic glory in the subject. But he was very interested in the work of H.G. Wells and read Origin of Species. But interestingly, he was the first Prime Minister to have a scientific advisor constantly at his side. One of the legacies that we look at in the show is how that appointment of a scientific advisor became common in every government after Winston Churchill's first term as Prime Minister. Churchill was very visual, and Lindemann and a group of his scientists called the S branch brought together science in a very visual way, looking at graphs. If we just walk around the corner, I can actually point one out to you so I can describe it. So he had his own statisticians who brought together information looking at cargoes lost at sea, the stocks of food types, looking at bacon and ham and cheese, things that Britain really depended on as imports. And the way that they depicted this information was using these very colourful graphs, as we can see here.
These look like the kind of infographics we see in the papers today, except they look hand-drawn and coloured in with felt-tip pens.
That's absolutely correct. And this is actually the first time that these graphics have been in an exhibition, and they come from the Churchill archives in Churchill College in Cambridge.
So let's go and have a look at some other things.
Rear Admiral Torless, who was in command of the operation, and Dr. Penny turned to watch the great cloud after its initial blinding flash was over.
We're now in the section called Health and Nutrition. So let's have a look at these two people here, Robert McCants and Elsie Widdowson. Tell me what they were up to prove whether you could or couldn't live successfully on rationing.
Well, they were two nutritionists. Just before the outbreak of the Second World War, they were working at Cambridge. They were interested in the nutritional value of food. And when it looked like war was on the verge of outbreak, they led the team of willing volunteers and actually tested the effects of a reduced diet, and they did this by heavily reducing their intake of food and then subjecting themselves to rigorous exercise in the Lake District. Their important finding is that they were concerned that there might be calcium deficiency if the British public didn't have enough milk and cheese, which is what they depended on imports. So they suggested putting in calcium carbonate or chalk into bread, and that's something that continued long after the Second World War.
I think someone put calcium carbonate into the meal I had out in the restaurant last night, judging by the way it tasted. That was Rachel Boone. She was showing Kat around the rather excellent, if we may say so, new exhibition on Churchill and science at the Science Museum in London, and it runs until the middle of next year. You're listening to The Naked Scientist with me, Chris Smith, and also with Kat Arney, and on to our main topic for this week now, which is plastics.
Plastics play an important role in almost every aspect of our lives. Just look around you now. Maybe you can see a toothbrush, a car steering wheel, toys, pens, food packaging, kitchen equipment, lunch boxes. The list is endless. Plastic is everywhere.
And that's just what Kat's brought into the studio to snack on while she's doing the show. Now, with us to lift the lid, if you will, on what plastics actually are and how they work is Cambridge University's Athene Donald. Hello, welcome to the programme.
Hello.
Good to have you with us. I suppose the logical place to start should be for us to address what actually is a plastic.
To me, as a physicist, I would probably call them polymers. They're long-chain molecules. Most simple things around us are small molecules, so something like water is just H2O, two hydrogen atoms and an oxygen, whereas polymers are long chains, many, many atoms long, as it were. And polymer means many units, so that they have blocks of units which repeat all along the chain.
And by changing the chemicals that are in that chain, you can get different things that behave differently or have different properties.
Absolutely. So the simplest is polythene or polyethylene, which is just a repeat of CH2, so one carbon and two hydrogens. And the carbon atoms join together to form these long-chain molecules. But other polymers are much more complicated than that.
Now, you've kindly agreed to show us a chemical reaction that revolutionised the lives of women everywhere with the creation of nylon stockings back in the sort of 40s and late 30s. But you're going to do the chemistry, Athene, here in the studio for us to make some nylon. We won't make stockings, but can you talk us through actually how this works and what you're going to do?
What I have in front of me are two glass bottles, each a litre in size. These are clear, transparent fluids I've got. One is hexamethylene diamine in sodium hydroxide and water.
Easy for you to say.
Well, I can read it off the label. And the other one is sebasyl chloride and hexane. So solution A, that first one I said, and I'm not going to repeat it, I've already got a small amount in this glass vial.
You've got literally a centimetre's worth in a little bottle beside the big bottle, haven't you?
That's right. I've just put a little in there, and I've got a glass rod with a hook on it. I'll explain why I've got the hook in a minute. And what I'm going to do is pour some of the second solution in, if I can get the lid off. I'm meant to pour this down the glass rod to try and form a stable layer between the two solutions.
We've actually got a liquid sitting on top of a liquid now.
That's right.
With the glass rod going between the two.
The second solution is less dense than the first one, so it floats on top. And at the junction between these two fluids, at the interface,
oh yes,
there's a reaction going on.
It looks like a spider web.
That's right. And I should be able to pull out this rope of nylon.
Wow. So literally it's coming from the layer between the two liquids. We've got what looks like a spiderweb material and you're drawing it out. It's now, wow, that's
I should
15, 16, 17 centimetres.
That's right. I should be able to pull it for a very long way. It gets thinner and thinner, and I have to pull it quite slowly because what I'm doing is picking up the nylon that's forming at the interface between the two liquids where the reaction is occurring.
What is the chemical reaction that's happening? Just in simple terms, what's going on here?
It's known as condensation reaction. So the two reagents mixed together, they give out, in fact, in this case, hydrochloric acid, HCl. And what is left is the two main bits of the chemicals joined together to make this long chain molecule. And there, it's broken. I'm afraid it's got to, about half a metre?
It's pretty impressive out of a tiny little bottle in the studio. This is just one type of polymer. So what sorts of qualities and properties do these sorts of plastics and polymers made in this way have that makes them special?
They are mainly pretty strong, they are very flexible, and perhaps the way we find them most useful is it's very easy to form them into different shapes. I'm old enough to remember enamel washing up bowls, and they always had to be round. But you could make a square or a rectangular washing up bowl out of plastic. You can form it into these shapes, and that's actually much less likely to tip or collapse under the weight of the water. So one of the key things is the ability to make into different shapes at quite low temperatures, not the kind of hundreds and hundreds of degrees you need, for instance, with metals.
When you refer to temperature, that's quite important too, because plastics do deform or change their shape when you heat them,
yes,
don't they? So why is that, and how can that be used?
As I say, these are long chain molecules, and in something like this example of the nylon rope, those molecules get all tangled up rather like knitting wool or something, bowl of spaghetti. But it means that the molecules can only move very slowly past each other. And so if you go to high temperatures, there's quite a lot of mobility. But at room temperature, most of these molecules are essentially frozen into place. So perhaps I can illustrate it with this second demonstration I've got, which consists of a plastic cup, the kind of thing you would have at a drinking fountain. But if I heat it up, so I've got a quite powerful hairdryer here, and if I heat it up, it will shrink back to the shape from which it was made. It will take a little while to get going. And you can see it's crinkling up. We're giving enough thermal energy to the molecules for them to retract back to the shape from which this cup was originally made. And the cup was originally made just from a flat disc, and you can see it there.
We have indeed got a flat sheet of plastic. It's about 5 or 6 centimetres across.
So it's the size of the base of that original cup, but the shape was... The cup was made by shaping it round some kind of mould at high temperature, and then cool it to room temperature, and it will stay in that shape. There's nothing that's going to make it change shape at room temperature.
Because those chains of molecules cannot slip past each other until they're made hot enough again.
That's right, yes.
Now, the one thing that people are always telling us, though, is that if I dump that in the waste paper basket, I've got a problem, because it then is not going to break down anytime soon, isn't it? So that must be one aspect of plastics. Whilst they're very useful, they're very durable, we do have the downside that they don't biodegrade.
That's right. If you break it up into very small pieces, it sort of becomes much less visible, but most of the bugs can't digest them, essentially. One of the ways of making biodegradable plastic bags is really to mix in the polythene with starch, and the starch, which is natural, does degrade. And so you get just tiny fragments and you no longer see that bright orange Sainsbury's bag or whatever.
But the bottom line is, because the plastic contains molecules with chemical bonds in them that you don't naturally find in the environment, there are no bugs out there like fungi and bacteria that know how to eat that, so it doesn't break down.
I would say there are no common bugs. I wouldn't like to go quite so far as to say there aren't any, because bugs are amazingly clever things.
So there may be a plastic cup digesting bug somewhere, but they're not that abundant, or at least not as abundant as the plastic bug.
They're not yet in landfill, yes.
Athene Donald from Cambridge University, thank you very much.
Well, that certainly is a problem, and it's one we're going to address now, because according to the United Nations, global plastic production has gone from 5.5 million tonnes in the 1950s to 110 million tonnes in 2009. And because, as we heard, plastics are resistant to the processes that break down materials naturally, they can accumulate all over the place, and one place is in the oceans. Captain Charles Moore from Algalita Marine Research Foundation was the first to document what he dubs as the Great Pacific Garbage Patch. That's a huge floating mass of plastic that's been aggregated by the ocean currents, and he joins us now. Hi, Charles.
Hi.
Tell me about this garbage patch. What is it like, and how did you find it?
Well, I found it by accident. Returning from Honolulu to California, I took a shortcut through a area known as the Doldrums, or the North Pacific High, and saw repeatedly for an entire week small bits of plastic floating by, and decided to come back and measure it scientifically, and found, to my surprise, there was 6 times as much plastic as plankton floating on the surface in this area. So what you've got is a plastic soup. Now, that soup is bulked out with larger croutons of material. And this last voyage, I actually found a floating island that I walked around and did a kind of a tour. I felt like Captain Cook. I mapped it. I took its position. I named the coves on it. And, it was quite exciting for a plastic researcher to find a floating plastic island. But basically what you want to envision when you think of these garbage patches is the equivalent of hundreds of miles of harbor debris attached to each other, basically from a couple of hundred miles off the California coast all the way to China in the case of the North Pacific, which is my field of expertise.
So my question is, where has this all come from?
It comes from everywhere. We live in the age of plastic. Our lives have plastic in them from dawn until dusk. We're creatures of plastic age. They deliver our food, we wear them, we make our cars out of them. Alternatives for every natural material out of plastic, and alternatives for every manufactured material, from steel to aluminum to glass. All those natural materials that were formerly the basic building blocks of industry have now largely been replaced by plastic, and new ways of using it are developed all the time. The problem is recovery of the material has not kept pace with the creativity of the industry, and now China has embraced the throwaway lifestyle, Indonesia, Malaysia. We just have this material, very light, that is able to blow and wash into the sea, since the sea is downhill from everywhere, and we're not recovering it in any meaningful manner.
This sounds like quite a serious problem, but, it's in the sea. What harm is it doing? Is this actually damaging the ocean life?
I have proposed the hypothesis, which we're currently testing, and I think other scientists should get on board, that more animals are killed right now by plastic in the ocean than by climate change. The death toll is alarming. It's in the millions of creatures killed annually by entanglement, by ingestion, by becoming starved by this stuff. And not to mention the fact, all the runoff of oils and greases and pesticides sticks to plastic. Plastic is hydrophobic, water-fearing, but lipophilic, oil-loving, and all of our chemicals are oily, and they stick to plastic and then transmit through the food web. And now we're finding 11,000 pieces in the average diet of the shellfish consumer in Europe. We're finding in every gram of oyster meat and every gram of mussel meat in the Gulf of Maine 15 particles of microplastics. So it's now part of our food.
I mean, I guess the other question is, this is just one that's off the coast of the Pacific coast. Are there other aggregations of plastic like this in our other oceans, and is this a growing problem for us?
Yeah, I mean, there's an around-the-world race going on right now, and they're becalmed in the Indian Ocean, and so there's nothing for them to do, and so the reports are coming in of seeing plastic as far as the eye can see from all these round-the-world racers that would rather be dashing through the waves, but now they're becalmed and they're seeing all this plastic. North and South Pacific, North and South Atlantic, and the Indian Ocean all have these gyres, these subtropical gyres that act as accumulators for this plastic. We've now sampled all of them, and published a paper and found trillions of particles weighing hundreds of thousands of tons. It's a huge amount of plastic out in the ocean.
It certainly is serious stuff. Thank you very much. That's Charles Moore. And later on, we'll be hearing whether a giant aquatic vacuum cleaner might be a practical way to clean up all this mess in our seas.
Now, more realistically, though, in the meantime, to reduce the global impact of plastics and to save money, many countries now promote recycling programmes to keep plastics in circulation and out of landfill and the ocean. In Cambridge, where we are, recyclable waste, including paper, metal, glass and plastics, goes into special blue bins which are collected and then processed separately to general household rubbish. But what happens next? Hannah Critchlow followed her rubbish on its journey to and through the recycling plant.
I've just been food shopping. What's for dinner tonight? Well, let's take a look in the bag. Burger with kale, mushroom, fries, and a glass of wine. Followed by yoghurt, milk and a tin of prunes for my morning breakfast. My stomach's satisfied, but I seem to have immediately produced a lot of waste, all of which goes in my blue recycling bin. But what happens to this detritus now? Cambridge City Council serves over 50,000 households, including mine, and I met the men who pick up our rubbish for recycling on their morning rounds.
I'm Mark O'Deluca, I'm from Cambridge.
James Kamack from Great Shelford.
James Jennings from Cambridge.
How many bins do you empty each day?
Say around 1,000 to 1,200 at least.
Each day?
Yeah, each day, yeah. Blue bins we pick up around 12 to 13 tonnes a day.
You guys get quite a lot of exercise, don't you, running around?
Yeah, it keeps us very fit indeed, yes.
Do you know how far on average you might run each day?
Between 12 and 15 miles a day. Behind the lorry, trying to keep up.
I left these chipper chaps to continue their round and followed my blue bin waste 8 miles up the road to the next stage in its recycling journey.
Mark Shelton, I'm Waste Education Manager at Amy Thesper at Waterbeach. We're in the materials recovery facility at Waterbeach where we take 350 tonnes of mixed waste every day from the council's blue bin collections.
And we're stood in front of a very complicated looking football stadium sized pitch area of conveyor belts which are multi-layered, one on top of the other. So 350 tonnes of blue waste rubbish are zooming past on these conveyor belts every single day. How exactly are they being separated?
There's a range of different machinery that the conveyor belts feed into. So the first bit of machinery separates out glass. It's basically a crusher that crushes the waste, and then there's a series of vibrating plates that separate out the glass. The next stage is the cardboard separator, and that separates out old corrugated card like the large brown boxes, simply because it's much larger than everything else. It then passes to a machine that separates out paper, and that's called a star screen, which has got a series of revolving wheels in the shape of stars. The paper rides across the top of the wheels and the rest of the waste falls through.
A series of magnetic separators then removes the metal cans for recycling. We're now left with some very different plastics. My milk carton, plastic bag and film, burger tray and yoghurt pot. How are these all managed?
We've got 3 near-infrared separators, and they separate out the plastic on the basis that different polymers reflect different wavelengths of near-infrared light. So the plastic is moving along a conveyor belt. Near-infrared light beams are shone down on the plastic. There is a receptor that picks up the reflected wavelengths. That then works some air jets, and the air jets are able to blow different polymers in slightly different directions to separate them.
So we're standing now beside the near-infrared separator now, and in the background you can hear that puss-puss noise, which are the air jets. You've got a conveyor belt in front of us rolling very quickly. The plastics are coming along the conveyor belt and they're blown across a divide wall. The plastics that are being separated out by this particular piece of equipment, pots, tubs and trays, are being blown over the divide wall, and the other plastics are just falling straight down. And then the plastics that fall straight down will go to the next separator.
Mark and I moved away from the rubbish stench to a quieter place to explore the next part in the plastic journey.
Plastic's very light, so we want to bale it as compact as we can so that when we're transporting it in the lorries to the actual companies that do the recycling, the reprocessors themselves, we're using as little diesel as possible.
And so these bundles, these bales, look very similar to hay bales, although obviously they're made of plastic.
And they're a lot larger, yes. We need a forklift truck to lift them. We put them into lorries and they take the materials to different reprocessors, the people who actually do the recycling. The plastic bottles, the milk containers, fizzy pop bottles, go to a company called J-Plas, who are based in Corby, and they're able to turn the material back into food-grade plastics, which are used for food containers and drinks containers, so more bottles ready for refilling. Corby's one of our most local reprocessors. They're only about 50 miles away. The pots, tubs and trays that may well go to Europe because the industries that actually use that material to make new pots, tubs and trays, again, it goes back into food-grade plastics, are based in Belgium. And the plastic film may have to go slightly further, perhaps to Malaysia, again, because that's where the industries are that require that material. And that's used, obviously, instead of a raw material. And that is then made back into a range of different products. It could be new bags.
Plastic recycling seems to require a lot of energy. I asked David Mackay, who worked as Chief Scientific Advisor to the government on climate change, if it was all worth it. He jotted down some calculations and said that, as a guideline, to ensure recycling is nowhere near pointless, his rule of thumb is that waste shouldn't travel more than 600 kilometres by road or more than 6,000 kilometres by the more environmentally friendly method of ship or rail. Although he added that since plastic is made from fossil fuel, of which there's a limited supply, and reprocessing emits less carbon emissions than the energy costs of obtaining more oil to make new plastic, a few more transport miles could be added to the equation. Well, I've followed my plastic waste on its recycling journey. It'll be born as a new plastic product that I can use again and again. So I'll keep sorting through my rubbish for recycling, and Mark Shelton at Amy Kesby added that they were looking to send their sorted plastics to reprocessing plants closer to home in the future.
Hannah Critchlow reporting there.
You're listening to The Naked Scientist with me, Chris Smith, and also with Kat Arney. If you want to get in touch with us here at the programme, you can email chris@thenakedscientist.com or you can tweet @nakedscientist. You can also look us up on Facebook.
At the moment, plastics are produced industrially using oil as a raw material, but in future it might quite literally be possible to grow plastics on trees. With us to discuss the future of plastics is Karnik Tarverde. He's Professor of Materials Processing at Brunel University in London. So first of all, do we really need all the kinds of plastic that we have in our lives at the moment? Say, if I go to the supermarket, I might get a nice salad, I pick up a lettuce and a cucumber, and they're shrink-wrapped in plastic. Why are they packed like that?
Yes, I'm glad you mentioned cucumber, because that has some very interesting statistics. First, I'd like to mention that regarding cucumbers, there's a very interesting, informative book written by Laurel Miller and Stephen Aldrich. And they're veterans in this area. And the title of their book is, guess what? Why Shrink Wrap a Cucumber?
Oh, well, there you go. Why should we? Why do I need to use this plastic to do it?
Now, hopefully, I'll try and convince you why we do it. Now, if we shrink wrap the cucumber, it loses 1.5% of its weight in 14 days. But if it's not shrink wrapped, it loses 3.5% in just 3 days.
So basically, it's going off in my fridge faster if it's not wrapped up.
Yes, exactly. Yes. With shrink wrap, it has much lower carbon footprint. It has a longer life, and also wherever it's kept, really.
I guess this is a bit counterintuitive, because people may think, oh, plastic packaging, it's always bad. Why do we need it? And if it does keep our food cleaner and safer and better for longer, it's a good thing. But can we recycle this kind of packaging?
Yes. Now, first, let me mention that in the UK, we use about 10 million tons of packaging per annum.
That is a lot.
And there's a lot. Yes, it's a lot of material. But what we need to do is make sure that this material has a recycling life cycle. It's produced, it's used, and it can be professionally recycled and reused again.
But is there a limit to the number number of times say, that the shrink wrap from my cucumber can be recycled?
Yes, there is. But what we do is you can always replenish with some virgin polymer. And when you are recycling, it needs tender loving care. That means you need to have the temperature just right with some flow promoters and also some antioxidants, which will then extend the longevity of these polymers.
But assuming that no one's going to recycle all their shrink wrap ever and people will just chuck it in the bin, tell me about the work that you're doing to try and make plastics that are actually more biodegradable from natural products. Tell me about these. How do they work?
Yes, there are quite a range of sugars that can be used to recycle and also make new polymers.
We heard Athene talking about starch earlier. Is that
yes,
one of them?
Yes. In fact, Brunel was one of the pioneers in processing starch. And there are a couple of large companies that make loose fill plastic made out of starch. So it's excellent packaging. And it's taken over around 25% of polystyrene loose fill, which is excellent. But the polymers that are made out of plastic, recycled and also biodegradable is quite a big range now. But PET and polypropylene play a big role. And PET is from sugarcane, it's sugar. But the big advantage of that is that when you process this material, it has good barriers against volatiles, against carbonation material inside a liquid.
So you can store all kinds of things, all sorts of food and all sorts of products in this kind of plastic?
Yes, very much so. And again, it has as good a longevity as some of the bilayer materials that are being used nowadays. But biodegradable polymers are also playing a big role. There is a special polymer called polyhydroxyalkanoates. This has polyhydroxybutyrate and polyhydroxyvalerate. These are, again, sugar-based from plants, but generated through bacteria sources. And they are biodegradable. They will degrade. But also from nature works, they generate a polylactic acid from cornstarch. That is, again, biodegradable, but at much higher temperatures. So if it's in very large compost bins, then it will degrade in municipal compost bins.
Now, one thing that always concerns me about biodegradable plastics, I've got a nice drinking glass here in the studio. I assume this is not biodegradable.
No,
it's filled with water. I'm drinking out of it. I worry that it would just disintegrate on me.
No.
How stable are these plastics in their use?
They are very stable. In fact, say the biodegradables from polyhydroxyalkanoates, which one of my students is working, and there are other scientists in the UK and overseas that are working on these. They are very stable materials, and you need to treat them carefully. You need to process them at the right temperature. But once they are processed, they are as good as any polymer that can be used.
Then when you get them in the compost heap, that's when they degrade.
Yes, when the bacteria starts attacking it and breaking down, taking all the nutrition away, and eventually it ends up like soil itself.
All sounds like good stuff. Thank you very much. That's Karnik Taverde. He's Professor of Materials Processing at Brunel University in London.
Also with us this week, Athene Donald from the University of Cambridge, and also Charles Moore, who was the discoverer of literally an island of floating plastic out in the ocean. They're still with us and willing to take some of the fairly large slew of questions that have come in from the audience during the programme. Athene, let's start with this one, which is from Rashmi Suriwala, who's tweeted at Naked Scientists, who says, yes, I recycle, but I'm not sure if it's energy efficient. Does at least stop landfill, I suppose. But what plastics are recyclable and which are not?
There's a big variety. One of the problems with recycling plastics is that if you take different kinds of plastic and put them together, they don't mix at all well, so you don't end up with a good product. The ability to sort plastics, which you are hearing about, is really transforming that. So there is a variety, and it's a question of what end product you're trying to make, whether it's recycled plastic is good enough for it.
Thank you. Charles, Jen Fox has got in touch and said, I recycle in the hopes of preventing the plastic from pelletizing in the oceans. What is the process by which these plastics break down in the ocean and then turn into these micropellets, which then can damage animals?
Well, there's three basic processes. One is photodegradation, where UV rays cross-link the molecules and make them brittle so that it breaks apart very readily in wave motion. Another one is the seawater itself is very good at extracting the plasticizers that make the plastic supple. And the third mechanism that I think is much more prominent than has been given a role in this process is the biting of the material by sea creatures. Practically every piece of larger plastic that we pull up out of the ocean has the edges nipped off. And I think a lot of these small fragments are created by munching the edges of plastic as it floats in the ocean.
Well, it's interesting you say that, because we've also got a question from Enrique, who says, well, what happens to me when I eat, say, a mussel or an oyster which has been consuming water which has got these tiny particles of plastic in it, and those plastics are built up inside the body of the oyster?
It contributes to what we call the body burden of synthetic chemicals, which were basically unknown before 1950. All of us now have a very heavy body burden of synthetic chemicals. Plastic is very good at absorbing synthetic chemicals that have washed into the ocean, pesticides, herbicides, industrial chemicals, anything petroleum-based, preferentially sticks to plastic because it's lipophilic, oil-loving, and that desorbs in our digestive systems into us. So the body burden of synthetic chemicals in our bodies is increased by the ingestion of seafood that contains plastic.
Which is quite a worry, isn't it? Athene, we've got a tweet here at Naked Scientists. We recycle our plastics, the person says, recycle in inverted commas, but are they really recycled? How much can be recycled? I suspect less than most people think, this person speculates.
I think a lot of it ends up in landfill, but I think that doesn't mean that's how it has to end up. I think we could do a much better job. There's another aspect that hasn't been mentioned at all, that actually plastics coming from oil can in fact be burnt and get energy back out of them as if you're going back to the virgin oil. The trouble with this process is it's very effective if you have a sort of closed environment and very high temperatures. But if you do it at lower temperatures, then there are some nasty chemicals that can be released. And I think that's why people haven't gone that route.
Is it worth considering, or part of the equation, we regard plastics as bad because they're a use of a fossil fuel, oil, but while they're a plastic, they're not turning into carbon dioxide in the atmosphere and therefore contributing to things like global warming, for which we condemn fossil fuels. So are they therefore less of a burden or less of a bad thing than if you do burn them, or if you do turn the oil into petrol?
I think that's a very complicated question, and I certainly don't know the out-and-out answer. I think it depends on many different things, probably including which polymer it is. There are all these different aspects. Certainly, now oil is cheap again, people may be worrying less about the original material, but of course we do still have a finite amount of oil, and we should be worrying about what we're doing with it.
Athene, thank you very much. That's Athene Donald from Cambridge University. We also heard from Karnik Taverdi at Brunel and Charles Moore. Thank you all very much.
And now it's our question of the week. Khalil Thurloway has been getting sucked into this question from listener Paul.
Could vacuum cleaners be fitted to ships to suck up all the plastic? Alternatively, could we use solar-powered floating vacuum cleaners or charged terminals to attract these plastic particles?
I guess the ocean could do with a bit of a spring clean. One person who knows a great deal about marine pollution is Professor Peter Franks of the Scripps Institution of Oceanography. I floated the question past him.
Coincidentally, there's an instrument that does exactly what you propose. It's called CUFS, or Continuous Underway Fish Egg Sampler. It's a big tube attached to the side of a ship that sucks up water, which is then processed through a series of sieves to separate the fish eggs for sorting and counting by the scientist.
That's convenient. It appears this is going to be a rather short edition of Question of the Week. Or is it?
Turns out that it's an incredibly inefficient way to get the plastic out of the ocean. The ocean's huge, and systems such as these sample an insignificantly tiny fraction of it. Even if all the ships in the world had such systems, it would not make any difference to the amount of plastic in the ocean, and the increased fuel usage due to the drag of the system would increase the CO2 being pumped into the atmosphere, enhancing global climate change.
Okay, it looks like ship-based cleaning is out of the question then. But what about a purpose-built floating vacuum cleaner?
There have been several proposals to do this. The problem is that most of the plastic in the ocean is in tiny particles about the same size as the plankton, the tiny organisms that live in the ocean. So any attempt to suck up the plastic will also suck up the plankton.
Plankton is a crucial part of the marine food web, providing food for organisms as small as shrimp and as big as whales. Messing with the plankton could throw the entire ecosystem out of kilter. Not good. Using charged electrodes would be problematic too, as salt water has a habit of corroding metals extremely effectively, especially when they've got an electric charge. We also don't know what effects the electricity might have on plankton and other sea life.
That being said, it might be possible to drag lines behind ships to recover lost fishing nets and larger plastic items. Though this wouldn't solve the problem of the tiny plastic particles in the ocean, it might help to reduce ghost fishing by those lost nets.
Ghost fishing is a problem caused by abandoned fishing nets and lines, which drift around the ocean, trapping and killing organisms indiscriminately. Removing these would certainly help protect ocean dwellers from this grim fate.
The problem is that such systems will always affect the organisms of the ocean one way or another. The better solution, of course, would be to stop putting plastic into the ocean, or anywhere else for that matter.
No easy solution then. I guess it's back to the drawing board in the search for a way to clean up the mess we've made. Next week, we'll be taking a shine to this question sent in by Harsh Vardhan Banot.
Why do some things like petrol create a rainbow effect on the surface of water?
If you have any ideas on why oil and water might make a rainbow, you can email chris@thenakedscientist.com. You can find us on Facebook, tweet @NakedScientists, or get stuck into the debate on the forum. That's thenakedscientist.com/forum.
And that is it for this week. Thank you very much to Hannah Critchlow, Danielle Blackwell and Khalil Thurloway for their help with production. And do join us next week when we're finding out why we're passengers in our own bodies. Indeed, the bugs that live on us and in us outnumber our own cells by more than 100 to 1, and they play a critical role in keeping us healthy. Join us next time to find out how. The Naked Scientist comes to you from Cambridge University. It's supported by the Wellcome Trust